We have two special types of logs, two special bases that get their own name. And the first is base 10. When we have a log base 10, we have what we call a common logarithm. And common logs, we don't write the base for usually. So when we just see log without a base written, it's understood that that's base 10. The percentage of adult height attained by a boy who is X years old can be modeled by f of x equals 29 plus 48.8 log x plus 1, where x represents the boy's age from 5 to 15, and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 10? So we're plugging 10 in because x is the boy's age between 5 and 15, and 10 is between 5 and 15. So from our function, plugging 10 in, we would add the 10 plus 1 to get 11. And it's going to jump to the answer of 80%. But I'm going to backtrack, and I'm going to put this in the calculator and make sure it's right. Also walk you through how we would calculate this. We would want the log of 11 first. So I'm going to find log 11. That's about 1.04139268.5. And we can put that right in the calculator using the log button because it's the common log. It's a base 10 log because there's no base written. That's the calculator log button. We're going to leave that value in the calculator. We're going to multiply it by 48.8. And then we're going to add 29. I get 79.8199. So 79.8 is about 80. A 10-year-old boy has attained approximately 80% of his adult height. So the properties of common logs are going to be very similar to the properties of logs that we've looked at already. Log base b of 1 equals 0. Well, then the log of 1 is 0. Log base b of b equals 1. That would be similar to the log of 10 equals 1, because log without a base is log base 10. The inverse properties, log base b of b to the x equals x, would be the log of 10 to the x. And b to the log base b of x would be 10 to the log of x. In other words, the common log and the base 10 cancel each other out. Now, I said there were two special types of logs. And you probably have a button for this as well, the ln, the natural log. That one is a base e. So log base e, we say natural log instead, ln of x. And if we look at those properties, again, we're just replacing the base on the left with e. And then whenever we have a log base e, we change that to natural log. So the natural log of 1 would be 0. The natural log of e would be 1. The natural log of e to the x is x, and e to the natural log of x is x. When the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, The temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function f of x equals 13.4 natural log of x minus 11.6 models the temperature increase, f of x, in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 30 minutes. So we take our function and we want 30 minutes. Minutes is x, so plug in 30. How do we get to our answer here? Well, we're going to take the natural log of 30 on the calculator. We're going to multiply that by 13.4. And then we're going to subtract from that 11.6. I get 33.976. We want to the nearest degree, so that's going to be about 34 degrees. The temperature will increase by approximately 34 degrees after 30 minutes. And that's it for this topic. The objectives of this topic are use the product rule, use the quotient rule, use the power rule, expand logarithmic expressions, condense logarithmic expressions, use the change of base property. So we're going to let b, m, and n be positive real numbers with b not equal to 1. The log base b of m times n is the log base b of m plus the log base b of n. In other words, the log of a product is the sum of the logs. Log of m times n is log of m plus log of n. The log of a product is the sum of the logs. So if we had log base 6 of 7 times 11, that would be the log of the first plus the log of the second. Log base 6 of 7 plus log base 6 of 11. We have the log of 100x. That would be the log of 100 plus the log of x. And then the log of 100, that's a base 10. 10 squared is 100. The log of 100 is 2. So 2 plus log of x. So that's the product rule. The quotient rule is that the log of a quotient is the difference of the logs. Log of m over n is the log of m minus the log of n. Log of the top minus log of the bottom. So log base 8 of 23 over x would be the log base 8 of 23 minus the log base 8 of x. The natural log of e to the 5th over 11 would be the natural log of e to the 5th minus the natural log of 11. And then the natural log is log base e. So the log base e and the base e cancel each other out, leaving us with 5. 5 minus natural log of 11. And then my favorite is the power rule. The log base b of m to the p is equal to p log base b of m. In other words, the log of something that has a power, we can take that power and multiply it in front of the log. The logarithm of a number with an exponent is the product of the exponent and the log. So log base 6 of 3 to the 9th, we can take that power of 9 and we can bring it in front of the log. 9 log base 6 of 3. And even though it seems like there should be something that we can do to simplify with the 6 and the 3, there isn't. Natural log of the cube root of x. Well, we have to deal with things in terms of powers, not radicals. X cubed root is x to the 1/3. So the natural log of x to the 1/3, and we can take that 1/3 power and bring it in front of the log. 1/3 natural log of x. Log of x plus 4 squared. We can take the square and bring it in front. 2 times the log of x plus 4. And there's no way to expand that log of x plus 4. That's not log of x plus log of 4. That's what we would do if we were multiplying x and 4 in those parentheses. There's no rule for the log of a sum or the log of a difference. So to recap, we've looked at the product rule, we've looked at the quotient rule, and we've looked at the power rule. We're now going to use these as facts that we have to expand this expression as much as possible. Log base b of x to the 4th cube root of y. Well, radicals do us no good. Cube root of y is y to the 1/3. This is two things multiplied together inside the log, x to the 4th and y to the 1/3. So we can take a sum of two logs. Log of x to the 4th, log of y to the 1/3. Make sure you write your base b every time, even though I'm not saying it. We know that the logs we're dealing with here are base b. Then we could use the power rule. Take that 4th power, put it in front of the first log, take that 1/3, put it in front of the second log. 4 log of x plus 1/3 log of y. And we have now expanded this expression. Let's do another. Log base 5 of the square root of x over 25y cubed. Again, radicals do us no good. The square root of x is x to the 1/2. We're dividing two things inside this log, so we can take a difference of the logs, log of x to the 1/2 minus log of 25y cubed. And that 25y cubed, that's two things multiplied together inside a log. So we can take that second log and we can change it to the log of 25 plus the log of y cubed. Since we were subtracting this entire log, that means we have to subtract the entire expanded expression. And we're going to go ahead and rewrite 25 as 5 squared so that we can clearly see that we can take this 2 and bring it in front of the log. Log base 5 of 5 is just 1. We'll get there eventually, apparently. Let's continue to simplify. The x to the 1/2 power. We can take the 1/2 power and bring it in front of the first log. Then we can distribute the negative. And then log base 5 of 5 is 1. So this is just minus 2 times 1 or minus 2. Also, in case I didn't mention it, I don't think I did, the y cubed for the log base 5 of y cubed, the 3 comes down front of that log, 3 log of y. Now you can see in this problem, way back here at the top on the right, I wanted to say log base 5 of 5 squared is 2. And you could have made that 2 at that point. That would have been a 2, and then that would have been a 2, and then that would have been a 2, and it would have been a 2 in the answer. So there's no particular order that you can apply these rules in. As long as you're doing right things, you will get to the right answer. But the trickiest part of this problem was, since we were subtracting this second log, when we expanded the second log, we had to subtract the whole expansion. Distribute that negative. But all of our powers became coefficients of the logs. We used every one of our properties in this one. Just like we used our properties for expanding the logs, we can switch the rules around and we can condense them. If we had 2 logs added together, we can take the log of the multiplication, the log of the product. If we have 2 logs with the same base subtracted, we can take the log of the quotient. If we have a number times the log, we can take that number and raise it to a power. So condensing is writing as a single logarithm. If we have the log of 25 plus the log of 4, we're adding 2 logs of the same type together. That's the log of multiplication, log of 25 times 4, which is the log of 100, which is 2. Because log of 100 is log base 10 of 100, and 10 to the second power is 100. Log of 7x plus 6 minus log of x. That 7x plus 6 is just there to distract us, make us think we can do something with it when we actually can't. We don't have any rules for logs of addition. But we're subtracting 2 logs of the same type here. That would be the log of division. Log of 7x plus 6 over x. Two natural log of x plus 1/3 natural log of x plus 5. And that x plus 5 is just there to distract us. We don't have a rule for that. But we do have 2 logs added together here. Before we deal with that, we have 1/3 in front of that second log. So take that 1/3 and raise it as a power to the x plus 5. Same with the 2 log of x. Take that 2 and raise it as the power. Now, instead of 2 log plus 1/3 log, we have log plus log. That's the log of multiplication. The log of x squared times x plus 5 to the 1/3. And the 1/3 power is cube root. So the natural log of x squared times the cube root of x plus 5 is as far as we can take this. Why did we change the 1/3 power to the radical? Well, if we were going the other direction, we would change the radical to the 1/3 power. When we were expanding and we were given a radical, we changed that to a rational exponent. So going the other direction, whenever we have rational exponents, when we condense, we can write them as radicals. Finally, let's take a look at something called the change of base property. For any logarithmic bases a and b and any positive number m, log base b of m equals log base a of m over log base a of b. What? It means we can change to any base we want. In this instance, we're changing to a base a by taking the log of the big number over the log of the little number. The logarithm of let's try that again. The logarithm of m with base b is equal to the logarithm of m with any new base divided by the logarithm of b with that new base. So when I'm saying big number, little number, I mean physically big and physically little. Nothing to do with their absolute values or anything like that. The log of the new base of the big number over the log of the new base of the little number. We can use this to introduce the common log into the problem. We can use this to introduce the natural log into the problem by changing to base 10 or changing to base e. Log of the big number over log of the little number. Natural log of the big number over natural log of the little number. How is this useful? Well, here it says to use common logs to evaluate log base 7 of 2,506. This feels like a calculator problem, right? The problem is there is no calculator button for log base 7. We do have the common log button. So if we take the log, the common log of the big number, the log of 2,506, and we divide by the log of the little number, the log of 7, that gives us 4.021996154, 4.02 on the calculator. So the change of base allows us to use our calculators to actually find these values for any base by bringing it to the common logs, or as we'll see now, by bringing it to the natural logs. If I did the natural log button of 2,506 divided by the natural log button of 7, I get 4.02 again. And that's it for this topic. So inverses cancel each other out, leave us with what we start with. So for instance, the cube root is the inverse function of the cube function. Notice if we were to put in the line y equals x, it creates a mirror between the function and its inverse. New function it's going to have a horizontal asymptote along the x-axis. It's going to have the point 0, 1. And it's called the exponential function. F of x equals b to the x. B cannot be 1. B greater than 0. This is the exponential function. The reason b, our base, can't be 1 is because 1 to any power is 1. It wouldn't look like this. It would be a horizontal line through 1. But let's imagine it was two to the x. And for x equals -2, -1, 0, 1, and 2, let's start with 0. Anything to the 0 power is 1. That's where we get our 0.01 that's always in the exponential function. 2 to the first is 2. 2 to the second is 4. 2 to the -1 is 1/2. 2 to the -2 is 1/4. So to the left of 0, negative numbers, we keep getting smaller and smaller fractions. 1/2, 1/4, 1/8, 1/16, 1/32. They get smaller and smaller and smaller, but they never reach 0. That's why this is a horizontal asymptote. To the right of 0, the positive numbers, they're going to get bigger and bigger more and more quickly. 2, 4, 8, 16, 32, 64. The larger the number we're putting in for the exponent, the even larger the y value. Exponential function. It has an inverse. Called the logarithmic function. This one has its asymptote on the vertical axis, the y-axis. Instead of always having its point at 0, 1, it'll always have its point at 1, 0. And it looks like this. Rises very steep to the left of 1, 0, but then grows extremely shallow as we move to the right. I said that they are inverses. Notice there's the logarithmic function. If I put the exponential function right over it, 0, 1 would have the point. Notice visually, symmetric about the y equals x line, mirror image over this line. So visually we can see that they are inverses. But what exactly is a logarithm? Well, a logarithm is an exponent. Say it a couple times. A logarithm is an exponent. A logarithm is an exponent. A logarithm is an exponent. What do I mean by this? Well, let's say we have 2 to the third equals 8. This is a true exponential equation. The base is 2. The exponent is 3. So we can write an equivalent equation in logarithmic form. Log base 2, a logarithm is an exponent, and the argument of 8, the number that was left over that wasn't the base or the exponent, becomes the argument here. So the base 2 logarithm of 8 would be 3. A logarithm is an exponent. Logarithm is an exponent. So to evaluate a log, we look at the little base and we ask ourselves, what's the exponent that gives us this number? 2 to what power is 8? It would be 3. Four squared is 16. Base 4, exponent 2. So the base 4 logarithm of 16 is the exponent 2. 4 to what power is 16? 4 to the second power is 16. So these are saying the same thing. What would be the base 10 logarithm of 1,000? Well, base 10, the logarithm is the exponent, so that's what we're looking for. And it has to equal 1,000. 10 to what power is 1,000? 3. So since 10 cubed is 1,000, the base 10 log of 1,000 would be 3. There's always an understood number, no matter what we're doing in math. For instance, when we have the square root, we know that there's an invisible 2. If we have the number 10, we know that there's always an invisible 1 exponent on any number. If we just see the word log, this refers to the common logarithm, the common log. And that's base 10. So whenever we see log without a base written, we are to assume that the base is 10 because it's the common log. So what would be the log of 10? Well, the log of 10 would be the base 10 logarithm of 10. A logarithm is an exponent. 10 to what power is 10? 10 to the first. Because 10 to the first is 10. Let's write these log equations in exponential form. So here, this is the base 2 log. So in exponential form, the base is 2. A logarithm is an exponent. So the exponent is 4. And 2 to the 4th is 16. The argument, the number that's left. Log of 1 over 100 equals -2. We don't see a base. So what base is that? Base 10. The logarithm is an exponent. So the exponent is -2. 10 to the -2. The argument 1 over 100. So what's left? Base 7 log of 1 equals 0. The base is 7. A logarithm is an exponent, 0. Anything to the 0 power is 1. The argument is 1. So the log of 1 is always going to be 0 because 0 is the exponent that will raise any base to the number 1. Let's go the other way. 3 to the 4th is 81. Write it as a log expression. The logarithm is an exponent, so the log is going to be equal to the exponent of 4. Base is 3. That's our little number. The argument's 81. Ten to the 6th is 1 million. A logarithm is an exponent. So the log is going to be equal to 6. What's the base? The base is 10. We don't need to write it. That's just log. The argument is 1 million. Log of 1 million is 6. 6 is the exponent that raises the base 10 to the argument 1 million. 1/5 to the -1 equals 5. A logarithm is an exponent. The exponent's -1, so the log is equal to -1. What's the base on the log? The base is 1/5. Argument would be 5. Let's evaluate some of these. Log base 9 of 81. A logarithm is an exponent. What is the exponent that we raise 9 to give us 81? 9 squared is 81. 9 to the second power. If you can't think of it that way, then just put it in exponential form. The base is 9. The logarithm is an exponent, so we don't know what the exponent is, equaling the argument of 81. We know that 81 is 9 squared, so x is 2. The 1/2 base logarithm of 8 is what number? So ask yourself, 1/2 to what power is 8? This one might be a lot easier if we write it in exponential form. The base is 1/2. The logarithm is an exponent, so the exponent is unknown. This has to equal 8. Well, 8 is 2 to the third, which would be 1/2 to the -3rd. So we see that x has to be -3. Then I introduced exponential and logarithmic functions. An exponential function, something like f of x equals some base to the power of x. And this will always have the 0.01 on it, because anything to the 0 power is 1. It'll always have 0, 1. And it has a horizontal asymptote on the x-axis. So exponential functions look like that. And actually, let me draw that a little better. Exponential rises steeply. This opposed to a logarithmic function, which is something like f of x equals a log of some base, the variable x. These are inverses. So since the point 0, 1 is always on exponential, the point 1, 0 is always on log. That means that the log of 1 is always 0. But 1, 0 is a point here. This one has a vertical asymptote on the y-axis. And it looks like this. Raises very steeply until it gets above the y-axis, and then it kind of slows down. Something to keep in mind about these is that just like any other function, we can move it up, down, left, or right. So let's say, for example, instead of this being b to the x, let's say it was 4 to the x. We can use our general shape, knowing that we have our horizontal asymptote at the x-axis and our always point of 0, 1 for exponential, to graph a new function. F of x equals 4 to the x plus 5 minus 2. Just like what we did at the beginning of the semester. Subtracting 2 from the function moves it down 2. So instead of the horizontal asymptote being here, it'll be down here. And x plus 5 adding to the x moves us left 5. So instead of our point at 0, 1, the point moves down 2, left 5. New graph looks like this. What would be the domain and range of the new graph? Well, from left to right, we'll always have x values. So the domain is all real numbers, negative infinity to infinity. But the range, negative infinity to positive infinity going up the y-axis. This graph doesn't have any y until it gets past -2, and then it'll have a y value forever. So that would be domain and range. All things we did earlier in the semester with other functions, now we can also do those with the shape of an exponential function. Adding or subtracting to the entire function moves it up or down.
Adding to the x moves us left, subtracting from the x moves us right. And then we look at domain and range, from negative infinity to positive infinity, left to right for domain, from negative infinity to positive infinity, bottom to top for range. So nothing new in the concepts, but we can apply it to our new functions. Same with a logarithmic function. We would take that shape. And pick it up, move it up, down, left, or right, depending on what the function tells us to do. Back into review. What is a logarithm? Remember, a logarithm is an exponent. And we can use this to go back and forth between log notation and exponential notation. For example, if we had log base 6 of 1 over 36 equals -2. The log is an exponent. The base is 6. So base 6 exponent -2 equals, well, the only thing that's left, the 1 over 36. And we know this is a true statement. And since that was a true statement, we'd hope to get something that's true. We can use that fact that a log is an exponent to rewrite it in exponential form. Remember, the base is the little number by the log. And if the log is an exponent, this log is -2. The exponent is -2. What about going in the other direction? If we have 5 to the -2 equals 1 over 25, base 5. So we would write log base 5. A logarithm is an exponent. The exponent is -2, so this log is -2. And what goes here? Well, the thing that's left, 1 over 25. So, a couple things to keep in mind. If we just have something like the log of 1,000 with no base written, recall that that is log base 10. So these are the same thing. When we don't see a base, that's base 10. There's another special type of log. And this one is shown as ln. So for instance, ln of 2. This is called the natural log. And this is the same as log base e. So these are the same thing. When we have a base e logarithm, that's the natural log that we write ln. And e is a special constant that's used in financial problems, continuous interest. E has a value approximately 2.71828. It goes on and on. So base E logarithms are natural logs, ln. We have some properties of logs that we're gonna want to go over. Log base B of x times y is log base B of x plus log base B of y. This is the product property of logs. And it's just if we have the log of two things multiply together, we add the logs. A logarithm is an exponent. When we have the exponent of two bases multiplied together, we add the exponents, we add the logarithms. That's where that comes from. It comes from our exponent rules. The log of two things multiplied together is the log of the first thing plus the log of the second thing. And what if we were talking base 10? The log of two things multiplied together is the log of the first plus the log of the second. What if we had natural log? Same deal. Doesn't matter what the base is. This property is always the same. The natural log of two things multiplied together. Natural log of the first plus natural log of the second. How do we use this? Let's say we had the log base 2 of 8x, and we want to write the logarithm as a sum. The log of two things multiplied together is the log of the first plus the log of the second. Simplify if possible. 2 to what power is 8? 3. A logarithm is an exponent. The exponent here would be 3. So we can use this property to simplify logarithms. What if we had the natural log of 5xy? Well, this property can be extended. This is 3 things multiplied together. So it's going to be 3 logs added together. It's the natural log of 5 times x times y. So that's the log of 5 plus the log of x plus the log of y. In this case, we were using the natural log. Similar property. The quotient property. Log base b of x over y, the log of two things being divided. It's the log of the first, the log of the top, minus the log of the bottom. So when we are dividing inside of the log, that would be subtracting the logs. Again, it comes from the exponent rule. When we're dividing two bases, we subtract the exponents. Couple examples here. How about the base 3 log of c over d? Well, that would be the base 3 log of c minus the base 3 log of d. What about the log? So that's the common log, base 10, of x over 1,000. That would be the log of x minus the log of 1,000. And this simplifies as the log of x minus 3. Because when we don't have a base written, it's base 10. And 10 to the third power is 1,000. The logarithm is an exponent. The exponent here would be 3. We also have a really cool power property of logs. If we're taking the log of something raised to a power, we can bring the power down front and multiply. So the log base b of x to the p, bring it down front and multiply. P times the log of b, the log base b of x. How would we use this? Well, let's say we have the natural log of the 5th root of x squared. We can write radical form in power form. Power over root. This would be the same as the log, the natural log of x to the 2/5. We can bring that 2/5 power down front and multiply. 2/5 natural log of x. Common log of x squared. Bring the power down front and multiply. 2 log x. Now, these 3 properties we've looked at aren't always just going to be there all at once or on their own. We can get them all at once. That's the point I'm trying to make. For instance, if we had the log of AB over C, we would add log of A plus log of B because of the multiplying on top. And then because we divide by C, we would subtract log of C. These properties can be used in either direction. We can use them to condense too. Let's say we were given log of A plus log of B minus log of C. First, make sure all the log bases are the same, and they are. Since we're just adding and subtracting, we can write it as a single log where we're multiplying or dividing. Log A plus log B means we multiply A times B. Subtracting log C means we divide by C. Looking at an example, log base 2 of z cubed over x, y to the 5th. Let's write this as a sum or difference of logarithms. This quotient means that we have log base 2 of z cubed minus the log base 2 of x, y to the 5th. Why did I leave this together? Why didn't I just make it plus right off the bat? Well, we would be subtracting the entire log, which means we're subtracting the entire addition. I wanted to point that out, that we need parentheses. And that minus would get distributed. So minus log base 2 of x minus log base 2 of y to the 5th. And again, not surprising because the x and the y to the 5th are both on the bottom. They're both being subtracted in the long run. Now we just need to take care of our powers. The z cubed, the 3 goes out front as multiplication. Minus log base 2 of x, minus, again here, the y to the 5th, the 5 comes out front as multiplication. Let's do another. The log of the square root of x plus y squared over 10. I'm sorry, this is a cube root. Log of the cube root of x plus y squared over 10. We can write this instead of as a cube root to the 1/3 power. X plus y squared over 10. We can take that 1/3 power and bring it out front as multiplication. We have division happening here. One-third is going to be times this log, which means it's going to be 1/3 times this difference. Log x plus y squared minus log of 10. One-third of log of x plus y squared. We can bring the 2 down front of this log. Log base 10 of 10, 10 to the first is 10, so this is all just 1. And finally, just multiplying it together, 1/3 times 2 is 2/3. Log of x plus y minus 1/3 times 1 minus 1/3. And we can't break up log of x plus y anymore because it's not log of xy. If it was log of xy multiplied, then we would make it a sum. But there's no log rule for the log of x plus y. We can go in the other direction. Let's say we had 3 log a minus 1/2 log b minus 1/2 log c. This would be the log of a cubed minus the log of b to the 1/2 minus the log of c to the 1/2 or the log of a cubed minus the log of the square root of b minus the log of the square root of c. So the log of a cubed over, because they're both subtracted, they both end up on the bottom, square root of b times square root of c. Square root times square root, we can combine. Log of a cubed over square root of bc.